Hello dear friends, I'll tell you everything you need to know to get started programming for STM32, so you can get started easily and without any problems. I've also prepared a series of instructions to help you set up the environment and start programming. In this video, I'll tell you everything you need to know to start programming microcontrollers. It's everything I wish I'd known 2 years ago before I started programming STM32. Everything you need to start programming. A board with the chip will be programming. Note, you need the original version, it's more expensive. A programmer, ST-Link V2. Altogether it costs $3, and that's enough to write your first program. Cube IDE. Download the free Cube IDE development environment from ST. There are many useful ST programs on their website. But for now, we are only interested in Cube IDE. The latest version doesn't have CubeMX built in, so we download it separately. I'll explain why it's needed later. This environment has no limitations and includes a built-in debugger and a database of many ST microcontrollers. But be careful, it only supports original microcontrollers, although it's possible to disable the chip ID check. I found a great seller of inexpensive development boards with original microcontrollers. Documents and textbooks. I recommend reference manual 0008 to get a basic understanding of the microcontroller's functional blocks, capabilities and memory structure. I recommend Kernighan and Rich's book on C if you are not yet familiar with the C language. For those who know Russian, I recommend Leonid Ivanovich Doroshka. I started learning the language using this book. It's just as good and in some ways even better. For those who already know C, I also recommend reading the specialized book on programming microcontroller C for embedded systems. It contains many useful links to further reading. Now let's write our first program. I installed the latest Cube IDE, and as it turns out, CubeMX was disconnected. So I installed CubeMX as well. I found the installation files on the ST website. You can download Cube IDE and CubeMX from this page. After installation, you need to configure a few settings in the CubeMX environment. First, let's choose the location where the libraries will be installed. I don't like the default path, so I moved it here. Examples are also stored in this folder. These examples are a good way to learn how to program ST microcontrollers. They contain many different examples for working with various peripherals. I changed the path and manually moved all the files to the new path. Now you can download the libraries needed to work with the microcontroller. I go to Manage Embedded Software Packages. The downloaded libraries are there. I install the libraries on my microcontroller. Incidentally, these libraries also contain examples of working with the microcontroller. Now I create a project. I select my microcontroller in the search. Here it is, the microcontroller installed on the blue pill. Now I configure port C13 to push-pull mode. According to the blue pill schematic, there is a diode on this pin. We'll control this diode programmatically later. Now I'll enter a symbolic name for the pin. This is so I can access the pin by its name. Let's add debugging capabilities to the STLink32. This will be useful when we begin exploring in circuit debugging. The schematic contains a high frequency crystal oscillator. Let's enable it as well. Now I'll configure the system clock. Here we'll simply ensure that the clock is generated by the crystal oscillator. Afterwards, I'll simply enter the maximum microcontroller frequency of 72 MHz. The microcontroller configuration is complete. As you can see, everything happened quickly. For comparison, you can try performing the same action using the LL library. This will take much longer. Now let's simply write one HAL library function, HAL GPIO toggle pin. We pass the pin and port as parameters using the previous assigned symbolic name. When creating a project using CubeMX, the HAL libraries are already included in the project. Now, before compiling all this, I'll make a few adjustments. Let's check that optimization is disabled. We don't need it yet. I'll also generate a few auxiliary files. I'll compile the project. Now I'll configure ST-Link. It just needs to be set like this. Now I'll connect the microcontroller according to the diagram below. I'll press record. If it works, the LED will blink, meaning you've successfully configured the environment and debugger. I have a custom syntax highlighting option in Cube IDE. You can change it here: Window, Preference, C, C++, Editor, Syntax Coloring. Here you can select the color of the element you are interested in and immediately see the result in the example below. I've left the instructions with all the steps. I followed at the link in the description. We've learned how to create a project and set up the environment, but how do we start writing our own programs? For beginners, I recommend studying examples with source code specific to your microcontroller. That's what I did. Set yourself a task. To start, I recommend choosing a simple one. For example, transferring bytes via SPI between two microcontrollers. I went to the Cube IDE libraries folder. We'd already installed them earlier. We found an example where this had already been implemented. We repeated this, learning how it works. I never simply copied anything without trying to change it or at least rethink it. And I wish the same for you. Understanding how it works is crucial. That's the whole point of learning. Then we set another task, such as transmitting data via SPI to another peripheral chip. This is more complicated. ST likely won't have an example. We look for an example, perhaps from the manufacturer, study it, and try to apply it to our microcontroller. It might need to be rewritten or the code found on GitHub, but be sure to check it out. And so on, task by task. Gradually, you implement your project. I usually draw up various diagrams and charts in which I describe the algorithms and tasks whose solution will bring me closer to completing the project. You might not have any ideas at first,
but as you study, the plans will become more precise and clear. The key here is to start. Learning to program happens while you are programming. Of course, you can take courses and read books at the same time, but I always learn by implementing my own project. It's more effective that way. In the modern world, there is no need to spend hours searching for information. Simply ask a neural network. You'll get excellent, high-quality answers to all your beginner questions. Just don't ask for a complete answer. The result may be unexpected. Be careful. When asking for help, you might not be given the best solution. Experience is essential here. That's all. Using the instruction above, you can implement any project related to microcontroller and programming.
I started programming microcontrollers about 4 years ago, after working as a locksmith in my spare time. I started learning, you could say, from the very beginning, assembly language programming. I made a few videos about it. I don't think you need to watch them. Knowing assembly language isn't necessary to program microcontrollers. I just studied it back then, and now I can't say for sure whether my understanding or working with microcontroller came from learning assembler or from experience. Generally, when I write C programs, I don't think about the sequence of assembly instruction my code will turn into. But if you want to write the fastest and most efficient code possible, talking up minimal memory, you can't do without assembler. But it's not easy to write in it, it's easier to make mistakes and difficult to find them. Assembly takes time, requires a lot of practice and a good understanding on the fundamentals. Fortunately, the memory capacity of modern microcontrollers allows you to avoid using assembly, which I recommend especially if you are a beginner. I recommend you study microcontrollers starting with the C programming language. It's a very powerful language. Everything is written in it: drivers, microcontrollers firmware, operation systems and application software. I don't know anything that can't be implemented in C. At the same time, this language is very simple, without any complexities or incomprehensible features for a beginner. In the future, you might be able to switch to a higher level language like C++. I haven't switched because C capabilities are sufficient for me. I don't feel any limitations. I think you'll understand me once you've learned the language well enough. When starting microcontroller programming, you absolutely must start with the basics, with our programming language. For example, here's how I started learning a language. I was applying to computer engineering. There were preparatory programming courses before university. It was all simple: Pascal, C, Delphi. That was the order the month-long course was structured. In my first year at university, we studied C. Then, in my second year, I spent 6 months studying Intel x86 architecture assembler, after which I successfully dropped out. After dropping out, I certainly didn't give up programming and continued to study science to this day. And, of course, the university course wasn't enough for me, although I learned a lot there. My first program were education tasks from the Kernighan and Ritchie textbook. Everything was for a PC. Now I understand that there is little difference between C code for a PC and C code for a microcontroller. Perhaps once you've mastered C well enough, you'll change your mind about writing microcontroller program altogether. It's much easier to start writing program that run on a computer. Simply because you don't need anything else beside a computer and the programming environment. Microcontrollers are more challenging in this regard, requiring more knowledge to get started, especially the STM32. However, ST has made it as easy as possible for beginners to get started with their software, extensive documentation, and numerous examples.
We've written our first program, but how do we start writing our own unique program? A common misconception is that STM32 is complex and unsuitable for beginners. It has a high entry barrier. This is no longer the case. What's commonly referred to as complexity is actually great capabilities, flexibility, and customizability. ST is currently doing a lot for developers. I don't know any other company that does more for developers using its product. For example, CubeMX makes it easy to configure the microcontroller itself, its peripherals, and its input-output ports. The excellent Cube IDE development environment allows for very flexible and comfortable development without any knowledge of the intricacies of compilation and linking. Much is done automatically, allowing beginners to get started faster. CubeMX not only allows you to configure the microcontroller and peripherals, but also connect ready-made libraries configured for the microcontroller. For example, connecting the FreeRTOS operating system would require a significant amount of time configuring and entering the necessary parameters, but here you can connect it with a single click. There are a huge number of guides, manuals, and instructions available to you. I'll give a few examples. I only show those that I've actively used for projects in the past. The main developer document is the datasheet. It shows all the peripherals used, all of which can be viewed in CubeMX. There's a block diagram and clock system explaining the operating principles. There's a power supply diagram. When routing the boards, I used its recommendations for connecting capacitors and power supplies. There's a maximum power consumption table. You can imagine how long this chip will last on battery power. This is the crystal oscillator circuit diagram. It provides some recommendations for selecting a crystal oscillator, but a link to AM2867 oscillator design guide for ST microcontrollers is provided. AM2867 provides the theory, calculations, and necessary checks for selecting a quartz crystal oscillator. Alternatively, you can simply select a crystal from the provided list. Both low frequency and high frequency crystals are listed here. The examples of tracing the inclusion of a quartz resonator turned out to be useful. There's a good step-by-step guide for selecting an oscillator. AM2834 discusses potential ADC issues. It also provides methods for improving ADC accuracy. It also provides a diagram for proper sensor shield grounding. It also provides a PCB grounding diagram and recommendations for connecting analog and digital grounds. AN3116 different ADC operating modes. AN5612 electrostatic discharge protection methods. STM32 describes the operating principles and implementation of a real-time clock. This is just a small part of the documentation. I could find instructions on the ST website for any STM topic I was interested in. The website also contains many other useful recommendations. You can learn a lot from these documents. ST manufactures and sells a wide variety of development boards. If the lack of hardware on the blue pill bothers you, you can choose from a wide selection to suit your needs. I don't buy those, they're not that cheap. Although they're actively used by YouTube creators. Besides programming, I also dabble in electronics. So I already have several STM32 boards I designed myself. I've been using them lately. I haven't used commercial debug boards in a while. However, as a beginner, I recommend starting with debug boards and a breadboard. However, using the application notes above and a little knowledge of routing, you can design your own PCB. I started learning this way myself until I started designing my own boards. I recommend the blue pill with the ST-Link V2 programmer. It allows both programming and debugging, and it's very inexpensive.
Now that we've set everything up, I'll show you how to use the debugger. Right now I still have the programmer and blue pill connected. If everything is configured correctly, I press the debug button. After that, the project name should be LED blink. When you first start debugging, you will see a window asking if you want to enable the debug window. This enables these useful windows. These are the processor core registers. There is also a window like this one showing the core registers and peripheral registers. I'll double click and set a breakpoint. I'll run execution until the breakpoint. The PC13 LED is currently off. We are interested in the GPOC registers. This is a list of registers that control the operating mode, reading and setting of output values. In our case, the LED is on port C, pin 13. We are interested in two registers. The first is output data register. Here you can see that pin 13 is set to 1. This means the diode is off, it's turned on by 0. I'll open reference manual 308, which I mentioned earlier. In the table of contents, we'll find the GPIO registers. This register shows the output value. The diode will be on when the ODR13 bits are 0. I'm checking to see if the diode turns on when ODR13 is 0. Yes, the diode is on. But we are interested in how this switching occurs. Let's move on to the function that switches the pin. The first function writes the ODR register value to the ODR variable. You can view the value of this variable in the window or add a new one. In ODR13 the value is currently 0, meaning the diode is on ODR 0. This line writes a value to the bit set reset register. What is this register? In this situation, if we write to bit set 13, pin 13 will be set to 1 and the diode will turn off. If we write to bit reset 13, conversely, pin 13 will go to 0. With this part of the function, if there is a 1 in ODR13, we'll shift it by 16 bits, thereby writing to bit reset 13 and resetting it. But we currently have 0 in ODR13, so if this value is 0, there won't be a reset. This part of the function inverts bit 13 and writes it to bit set 13. This means the diode will light. I'm stepping in the debugger. Yes, the diode is off. On the next pass, the bit will be cleared. This is the purpose of this function, toggling the pin passed in the parameters to the opposite value. This allows you to step through the program and observe change in the system. Now I want to show you how to enable the display of assembler instructions. Open the disassembler window by going to Window, Show View, Disassembly. I'll move the window to a convenient location. Now you can easily view all the instructions generated by the compiler and later executed by the processor. This would take a long time to explain, as there are quite a few instructions, so that's not the topic of this video. I wanted to show you how the C compiler implements code execution. I'll show you where these instructions are described. There is a program manual 0056 on the ST website. For example, we are interested in ALDR. It loads a word into a register. Using the address in register R7 plus 20 bytes, we write the value from memory to R3. R7 holds the stack pointer, and we usually move parameters passed to the function and registers onto the stack to preserve the execution logic. That's all I wanted to show you about debugging. I'm generally self-taught. University isn't about practical skills. It's about the ability to analyze information, the ability to extract information from the surrounding world, and the ability to make decisions based on that information. You shouldn't expect practical skill from university. You must acquire practical skills independently through experience, self-study, and experimentation. They are not something set in stone for centuries. Technology evolves along with methods, equipment, and tools. At university, you should master the skill of data analysis. That's the most important thing. Although I think you can learn this on your own with due diligence. Work, write, repeat, make mistakes, create, you will succeed. And of course, subscribe to the channel and like it. Bye everyone, until next time.